In this video, I'm going to discuss distillation. And so first, I'm going to start off with a little bit of boiling point theory. And so at equilibrium, the rate of evaporation is equal to the rate of condensation on the surface of the liquid. And so we have the vapor pressure here, which is less than 1 atmosphere, and then our external pressure is 1 atmosphere. And so there is less of this, well, there's the same amount going out as there is coming in of these molecules of whatever our solution is here. And that will remain the case until we get to the point where the vapor pressure is 1 atmosphere and the external pressure is 1 atmosphere. Or as I show over here, we can do sort of the opposite, where if we have this at, say, greater than or equal to 1 atmosphere and the external pressure goes down less than 1 atmosphere, then we will also have this start to boil and evaporate. But we can also have it be where if we increase the vapor pressure of our solution above the external pressure of the atmosphere, then we will also start see boiling occurring. And so this will happen if we heat the liquid up enough, which we will talk about here in a little bit. So we can have here, so this on the left is the water boiling point at high pressure. And so we see that the boiling point of water, so it starts at 100 where we have the absolute pressure at 0. So this starts going up and the boiling point of water increases as the pressure goes up. We're over here, this is telling us how far below the atmospheric pressure we are. So this is in millimeters of mercury. So 0 would be at atmospheric pressure, so 760 millimeters of mercury. And then this would be 660 millimeters, 560, so on, until we get over here where this would be at vacuum pressure. And so we see that the boiling point of water will decrease as we reduce the pressure. And so we can calculate the change in pressure with a change in temperature. So the change in the vapor pressure with the change in temperature using this equation right here. If we put our different pressures in here, and so this is our change in temperature, so say we start at this temperature and we want to see what happens to the vapor pressure of our solution when we change it to some new temperature, this will give us that change in pressure. And so as a rough rule of thumb though, at around 760 millimeters of mercury, which is atmospheric pressure at sea level, the boiling point of many liquids drops by around 0.5 degrees Celsius for each 10 millimeter of mercury decrease in external pressure. And so we can look at the change in vapor pressure as the change in temperature. So we're changing the temperature here, and this is the vapor pressure. So at 100 millimeters of mercury, we would have the boiling point here at 100 millimeters of mercury, and then the boiling point at 760 millimeters of mercury would have a vapor pressure right here. And so this is actually some real data here for a few different solvents. So we have things like diethyl ether, we have bromine, ethanol, water, octane, ethylene glycol, and mercury. And so we can see what the vapor pressure of each of these goes to as we increase the temperature here. And so they will all have lines that look very similar to this, where as we increase the temperature, the vapor pressure will start shooting upward at sort of an exponential rate. All right, and so we also want to think about what's called Raoult's law. If we have an ideal solution, which is one that has two or more perfectly miscible substances, and that does not have a change in heat or volume when mixed. So, for instance, if you have some pure water and pure ethanol, and you mix them together in 50-50 ratio, what you'll see is that the volume of the mixture is actually less than the addition of the two pure volumes because of the way the molecules sort of interact with each other. And so we could think of something like a beaker here that has, say, water on the bottom and ethanol on the top. So say we have these separated. These things are very miscible, so they wouldn't actually separate, but we can just think about this as a thought experiment. And so we have some volume here that is the two of them separated. And then when we mix them together, we will get something that looks like this that has a volume 2, and so we'll call this volume 1, where volume 2 is less than volume 1. And so we know this is not an ideal solution because when we mixed it together, we had a change in volume. But if we then have this one that's perfectly mixed together and we do another stirring or shaking or something, you're not going to see any change in the volume. And so we know that this is an ideal solution. And so Raoult's law says that the partial vapor pressure, so this P sub I, of a component of an ideal solution is the vapor pressure of the pure component, which is this P sub I star multiplied by its mole fraction. So we will get this, where the mole fraction is just the amount of that mole, so the percentage of that mole essentially in the solution. And so we can look at this here where on the left we have pure A and so no B, and on the right we have pure B and so no A. So this would be the vapor pressure of pure B. This is the vapor pressure of pure A. But when we start mixing them, we see that the amount of A goes down, so the total vapor pressure is also going to go down because the total vapor pressure is going to be the addition of those two, and it will go down until it meets right here at the pure B. So when we have these different mole fractions of these two substances, we just add them together to get the vapor pressure of the full solution. So let's say, for instance, we have a solution that is composed of 7 moles of solution A, which is a vapor pressure of 780 millimeters of mercury, and 3 moles of solution B, which has a vapor pressure of 790 millimeters of mercury. We then get the mole fractions this way, so we just add the two amounts of moles here, and for A, we just divide this by the total. For B, we divide this by the total. So we get 0.7 and 0.3. Then the partial vapor pressures will just be the vapor pressures of the pure multiplied by their mole fractions. And so we get these partial vapor pressures for each of those. We then use Dalton's law and add those together. So this is the vapor pressure of our full solution of A and B mixed together. We can also use this to calculate the composition of the vapor at the boiling point. And so to do this, we just take the vapor pressure and divide it by the total vapor pressure here. And so for our example here, we just end up with these two right here. So those are pretty much just the 0.7 and 0.3 that we started off with. So what this means is that if our vapor pressures of these two things are equal and we try to do a distillation, we will not be able to get any separation. If we have, say, A greater than B, then there will be more A in the vapor than B in the vapor, and so some separation will occur. And if the vapor pressure of A is much greater than B, then there will be much more A in the vapor than B in the vapor, and so a good separation will occur. And so in this video, I will be talking about simple distillation and fractional distillation. So we'll start with simple distillation. And so a simple distillation is just the process of vaporizing the liquid, condensing the vapor, and collecting the condensate in another container. So it uses the differences in vapor pressure, which is just another way of talking about the boiling point of two liquids, to separate them. And so this is what you will probably be using, especially if you are taking an organic chemistry class, where we are going to boil our solution right here. The vapor will move up. It will go into this arm right here where it'll go down. We have water flowing around the outside of this. That's a coolant, and so the vapor will condensate inside here, and then it will end up going into this other beaker right here. And so, as I said, if we have a single component solution, or if the two components of our solution have exactly equal vapor pressures, then what we'll see is that the temperature over time will just stay constant. So as you are boiling this, we have our thermometer in here to keep track of the temperature. the temperature will not change as we boil this off because the solution is going to just have the same boiling point the entire time. Whereas if we have a two-component solution that have similar boiling points, we'll see kind of a continuous increase in the temperature here. And so that's because, say, if A has a lower boiling point than B, then we will start boiling off the A first, and the vapor will start having more and more B content in it as we go through time. And so the boiling point will start approaching that of B rather than A. And if we have a two-component solution with very different boiling points, then what you'll see is that you'll pretty much boil off all of the A, and then once all the A is gone, then the temperature will go up pretty quickly, and then we will start boiling off the B. And so when a two-component system has a large boiling point difference, as is often the case when distilling like a water and salt system, so salt has a much higher boiling point than water, the temperature remains constant while the first component distills, so say the water in our saltwater system, and this results in a relatively pure substance. Substances with more similar boiling points will require fractional distillation to obtain a decent purity, which I will talk about here in a little bit. So if we're still looking at our simple distillation, let's say we have something that has 80% B and 20% A in it at this point W. And so we heat this up so that we get here, which is the boiling point of this mixture. What we'll see is if you then look at what's in the vapor, it will actually have a composition of here at Y. And so we go down here and it will have this composition. So because A has this lower vapor pressure, this lower boiling point, the vapor will be mostly A and less B. And so that's how the distillation works, is that the vapor is going to contain mostly the more volatile substance rather than the one with the higher boiling point. And so we can boil off the stuff that has the lower boiling point. So we see here at temperature T, so that's what we have here at this horizontal red dotted line. The intersection at X indicates that liquid of composition W will be in equilibrium with vapor of composition Z, which corresponds to the intersection Y. So like I said, this is the composition of our liquid here, so about 80% B and 20% A, but the composition of the vapor coming off of it is going to be right here at Y, so that's somewhere around here. So at pure A or pure B, the vapor and liquid curves meet, and so the liquid and vapor will be pure A or pure B. So that's just saying if we had this, if it was 100% B and we were boiling it, we would just have the liquid and the vapor be 100% B, and the same would go for A. So a mixture of A plus B, the composition W will, when heated, increase the temperature until the boiling point of the mixture is reached. So that's right here. And at temperature T, the liquid boils and the vapor composition, thus the vapor has more A than the liquid, which makes sense since A has the lower boiling point. And so if we have two substances with very similar boiling points, then we want to use fractional distillation. So this uses a fractionating column that subjects a mixture to continuous vaporization condensation cycles as the material moves through the column. Horizontal lines on here, so that would be something like this line right there, represent vaporization. So for instance, a liquid with 45% A, so that would be at L3 here. So we have 45% A, so that's right around here. So that's L3 on the diagram at 72 degrees Celsius. So if we're looking at right around here, yields a vapor with 65% A at equilibrium. Thus, the vapor is richer in A than the liquid. And so the vapor would be this right here. So this is our liquid composition, and this is our vapor composition. And so we have more A in the vapor than we do in the liquid. So the vertical lines represent the condensation steps of a vaporization condensation cycle. So the composition does not change as the temperature drops on condensation. So the vapor at V3, for example, gives a liquid of 65% A with a drop in temperature. So this is our vapor after this has boiled off. And then when it recondensates, it goes down to here. And so the composition of the liquid that has recondensated is not different from the vapor. But then we do another vaporization going over here, which does have increased amounts of A in it, and then that recondensates, then it vaporizes again, recondensates, and so on and so forth. And so that kind of looks like this right here. So this is our temperature gradient. We're in the flask. It's the hottest. Once it starts going up the column, it starts cooling down. And so we have here in our flask that our liquid is only 5% A. And so the vapor is going to be 20% A. Then that moves up the column a little bit. And so it recondensates at L2. So now it's 20% A in that condensate. And then it re-vaporizes to 45% A. It moves up the column a little bit more. Then it recondensates to 45% A. Then it re-vaporizes, and so on and so forth. So moving up this column like this until we get to the top where we have a vapor of 97% A. We could maybe have that recondensate again. And so you could kind of keep moving these lines down closer and closer until you get to 100% A. And so what I'm showing here, this right here, is the fractionating column, which is that part of our distillation apparatus. So we see it has these beads inside of it, which are going to allow the vapor to recondensate on those beads and then re-evaporate as it moves up the column so that we get this fractional distillation. And so we want to think about the efficiency of the column because, like I said, if we want to keep kind of moving this over and over sort of arbitrarily close, we want our column to be as efficient as possible. And so when we think about the efficiency of the column, we think about what are called the theoretical plates of the column. And so what that means is we take our column here, so this is our column, and we sort of separate it into these plates like this. And so I have that over here, so this has 14 plates. If we double that again, we get 28, then 56, then 112. And so the more efficient the column is, the more plates it has, because we can think of each of these plates as being a place where another condensation then revaporization process is occurring. So if we have more plates, then we have more condensation revaporization processes occurring in our column. And like I said, these are theoretical plates. They're just a way of theoretically thinking about the column. They're not actually going to be splitting the column up into these plates. The number of theoretical plates is related to the number of vaporization condensation cycles that can occur as a liquid mixture travels through the column. And so, like I said, each plate is going from some level here to some short level, some small level above it. And so we want to sort of think of this as going to zero. If we wanted to get sort of perfect efficiency, we would end up just having infinitesimally small plates. But we can see here with these theoretical plates, so if we have just one, then the boiling point difference between each one is 108 degrees. Then as we go up, we get to 100, so the boiling point difference between them is 2 degrees here. And so that tells you that every time you move up one of these, the boiling point should change by 2 degrees. And so, as I said, the more plates you have, the more continuous the change in boiling point is going to become. And so that's why we want to think of having the most efficient column as being one that has the most theoretical plates. And so there are various things you can do to try and increase that. So one of them would probably be to have smaller of these little beads inside of it so that you pack them in more, which is going to have its own problems because it's going to start making it harder for the vapor to actually move up. But these are all very theoretical considerations that we can take into account when we're trying to get a more efficient column. All right, so one other thing to think about here are what are called azeotropes. So some mixtures of liquids, because of attractions or repulsions between the molecules, do not behave ideally. and so they do not follow Raoult's law. So this is shown in minimum boiling point and maximum boiling point diagrams, which I have right here. So what we end up having are these points here where we get the maximum or minimum boiling point, but it's not at a pure substance. And so when you try to distill these, you're only ever going to get this or this coming off as the as acting like the pure substance essentially. And so you can't use distillation to completely separate those. So an azeotrope is a mixture with a fixed composition that cannot be altered by either simple or fractional distillation. An azeotrope behaves as if it were a pure compound and distills from beginning to end of its distillation at a constant temperature, giving a distillate of constant azeotropic composition. So these are some common azeotropes here. So this top one are a common minimum boiling point azeotropes. So for instance, ethanol and water, when you try to distill that, you will get 95.6% ethanol and 4.4% water as acting like your pure substance. And there are other ones here like benzene water, ethanol, and so on and so forth. Then these ones are common maximum boiling azeotropes. And so again, we see like with the acetone chloroform, if you try to distill that, you're going to get something that's 20% of the acetone and 80% of the chloroform acting as if that is a pure substance. You're not going to get it any more pure than that using either simple or fractional distillation. But these azeotropes can be exploited for a certain type of reflux here. And so we have the vapor coming up, it comes into this right here, and then it condensates and goes back down in here. And so these two things are miscible as vapor, but immiscible as liquid. And so they separate. And so whatever is on top here will start overflowing and going back into your reaction vessel here. And that's something you can do if you are trying to use Le Chatelier's principle to push a reaction towards products. And you have, say, a product coming out here and ending up down in this part of the vessel so that we're removing that product and then pushing this, say, maybe a reactant back into it so that we can exploit Le Chatelier's principle to push a maybe inefficient reaction towards products. And so that is something that we can actually use this azeotrope for. The simple distillation and fractional distillation are the ones I wanted to cover today, but ones I wanted to mention, so these other types of distillation, there's what's called vacuum distillation, and so that's just reducing the pressure in order to lower the boiling point, and so this is good for substances that have a high boiling point. There's also something called a steam distillation, which is good for distilling a heterogeneous mixture of immiscible liquids. So say you have some kind of colloidal mixture or something and you want to distill it, you can use steam distillation. All right, but anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.